I trust you did well on that quiz. Terms definition section of your notebook. And going to kind of change gears and kind of build on what we were just doing with all of these constructions. I'm going to introduce you to a word. We're going to use this here. We'll use it again in senior year pre-calculus. And that is this term locus. Locus. Not locust, like the little grasshopper critter that eats everything and that got eaten by John the Baptist with wild honey. Not that kind of locust. Locus, L-O-C-U-S. The plural is loci. So if we refer to more than one locus, we have a loci, kind of like radius, radii, locus, loci. The locus, here's your definition, is the set of all points, and only those points. The set of all points, and only those points that satisfy a given condition. The set of points, and only those points that satisfy a given condition. One more time. The set of all points, and only those points that satisfy a given condition. You need to note there that there are two key qualities of a locus. Two key qualities of a locus. First of all, a locus is inclusive. A locus is inclusive in that every single point that could possibly satisfy the condition must be included in the locus. A locus is inclusive. We talk a lot about inclusivity in today's culture. Hey, if you're qualified, you ought to be included. All right, that's inclusivity. A locus is inclusive. But a locus is also exclusive. Only those points that satisfy the condition may be included in the locus. So a locus is a description of a set of points that satisfy a condition. It must include all points that could possibly satisfy the condition, but it must exclude anything that does not satisfy the given condition. Yes, sir?
What do you mean by
I'm about to go through this, okay? So I had you copy down the definition. Now let me explain. So for instance, and again, if you're watching on YouTube, you're going to have a hard time picturing this, but just picture a room that you're in. For those of you in here, let's picture this side wall. And let's suppose I wanted a spot in this room that is 6 feet away from this wall. Am I standing 6 feet away from this wall? No. We'll have to use a little bit of imagination here, but imagining right about here appears to be about 6 feet from the wall. Is this the only point in the room 6 feet from the wall? No. There's a lot of other points. For instance, move this desk out of the way here. Maybe this is also 6 feet away from the wall, right? Are these the only 2 points 6 feet away from the wall? No. There's a whole lot of points that could be 6 feet away from the wall. Is Ethan 6 feet from the wall?
No.
Not quite. So Ethan's excluded. He doesn't satisfy the condition of being 6 feet from the wall. Do we see how it must exclude Ethan? Mm-hmm. Jamie's also not 6 feet from the wall. She's too far. So Jamie doesn't satisfy. I probably, at the moment, don't satisfy, but if I came right about over here again, okay, now I would satisfy that condition. And in fact, if I wanted to find every single point in this room that was 6 feet from the wall, what would I end up with?
An infinite number of points.
Right, that would make what shape?
A straight line.
A straight line. I would get a straight line. Now let's think about the straight line for a minute, because in this room, if I were drawing them, for instance, on the floor, I could draw a whole lot of straight lines, couldn't I? Right? But this straight line would have to run parallel to the wall and would have to remain exactly 6 feet away. Now, if you're thinking in 3 dimensions, we'd actually have a plane, an infinitely thin plane running from wall to wall, right? It would basically look like another wall, except it'd be so thin you could see through it, that would run 6 feet away, but it would run parallel, wouldn't it? That would include every single point 6 feet from this wall in this room, but it would exclude anything else. Does that make sense? How about this? What if I wanted all the points, the locus of points, 3 feet away from my lectern? Well, am I 3 feet away from my lectern?
About.
maybe let's think of the stand of the lectern. Might be a little bit easier. But I feel like I'm about 3 feet away now. But is this the only point 3 feet away? No. I could come right about here and be 3 feet away. Right? Or, not Ethan, he's too far. But maybe, hi Ethan, maybe right here would be 3 feet away. You realize this is not 3 feet away. This is excluded from the locus. This doesn't count. It's not satisfying the condition. But over here is too far. It doesn't satisfy the condition either. If I wanted every single point 3 feet from the stand of the lectern, what would I need? A circle. Now, if you're thinking 3 dimensions, it'd be a cylinder, right? But a cylinder, or let's just go plane geometry here. Let's go circle. I need a circle, but not just any circle. I mean, I could draw a whole bunch of circles in this room, right? I would specifically need a circle, class, that...
3 feet away. Okay. Circumference of 3 feet.
Circumference of 3 feet? I think you mean... Not circumference of 3 feet. Radius of 3 feet, right? Well, I could draw a whole lot of 3-foot radius circles in this room. But I would need to draw a circle with a radius of 3 feet that specifically has this lectern as its center point. Do you see that by describing the circle in that way, I have included every single point 3 feet away, but only those points. If I just had a circle with a 3-foot radius, I could make a circle with a 3-foot radius that cuts through Ethan and Jamie, right? But they're not 3 feet from the lectern. So I can't just say a circle with a radius of 3 feet. It would have to be a circle with a radius of 3 feet that has the lectern as center. I've now made it very exclusive, only those points. But I've also made it very inclusive. It's not just the 4 random places I happen to stand, it's all the points that would satisfy. Does that make sense? What if I wanted, yes sir?
So, theoretically, if you were below it, 3 feet below it, you would still be 3 feet away.
Well, I did say in this room. So,
It's fine, 3 feet above.
so if I were to somehow hover 3 feet above,
in the air,
so I guess technically, right, if we were, now,
But that's
the
taking
hard
3
part
feet.
would be the stand of this, right? So you'd actually end up with a domed cylinder, like a silo type thing, if we were thinking 3 dimensions. Since, again, sticking with plane geometry, it would have to just be the circle. But yeah, I mean, if you were thinking 3 dimensions, you know, pick a random point in the top of the lectern. Now it'd be a sphere, right, about it. But yeah, the sticking with plane geometry was thinking in terms of the circle there. But yes, you would be correct. What if I wanted to think about all points in the room that are, let's say 4 feet away from this row right here. 4 feet away from this row. Well, Ethan looks like he's about 4 feet away from the row, but he's not the only one, right? Who else is 4 feet away from this row, class?
Anyone on this row?
Genesis, Kendall, if I were to sit right here, I would be, right?
Them.
What?
Them over there.
Oh, and them over here. Yeah, I've got to include them as well. Because they would also be, assuming that it's actually about 4 feet, they would also be about 4 feet away from this row, wouldn't they? I can't just talk about this row. I have to talk about this row. Now, technically, you would actually have to kind of round off staying 4 feet away, wouldn't you? You'd have to put a little semicircle at the end, wrapping 4 feet away from that. But if we imagined this to just be a straight line, let's just say it goes all the way to the ends of the wall, you would say I've got what shape for 4 feet away from this row? I'd get 2 lines. Each of them would have to be parallel to this row, but I could draw a whole lot of lines parallel to this row.
Wouldn't they be equal? No, they wouldn't, because they can be infinitely long and one cannot be infinitely long.
Well, again, if we're saying line, technically line would be infinitely length, or in this case, it would run from front wall to back wall. So that I can always add more desks to each of the rows. But assuming the row went from front to back, I'd have 2 lines, right? Each one would have to be parallel to this row. What else would have to be true? They both have to be 4 feet away, don't they? And they would have to be on opposite sides, wouldn't they? So 2 lines, one on either side of this row, each of them 4 feet away from this row. And of course, parallel. I don't think I mentioned that yet. Parallel to this row. Do you see how by being very specific in our wording, we can describe a full locus? Remember when I said 6 feet from this wall? I did mention in this room. But you know, if I hadn't mentioned being in this room 6 feet away, I'd have to also account for people standing at the locker over there, wouldn't I? Because that would also be 6 feet away, wouldn't it? Yeah, that's the idea of the locus. Now, I would say that spiritually speaking, salvation is very much a locus, is it not? Anyone who satisfies the condition trusting Christ as Savior, asking for His forgiveness of sins, can be saved. Very inclusive. But the part the world hates is it's also very exclusive, isn't it? Because we believe the Bible clearly teaches if you don't accept Christ as Savior, nothing else you do really matters. It's not enough to get you to heaven, right? So salvation is very much like a locus, though in a non-geometric sense, in that it's inclusive to anyone who wants it, anyone who can satisfy the condition, but also exclusive in that those who do not fall into that satisfying that condition or conditions would be excluded. Turn your textbooks, if you would, to page 173. Now let's think through some more of these locus problems. It's a deeper way of thinking, isn't it? Okay, so I'm going to try to stretch your brain a little. I know it's a Friday and you're tired.
Friday morning.
And I show no mercy. Here we come at you with the locus problems. All right, so here we go.
I have no brain.
Page 173. And let's go and take a look at exercise 3.29. There at the bottom of page 173. It says, where do you find all points in the front wall of your classroom? Notice that narrowed it down. Nowhere else in the room matters except the front wall now, right? That are 3 feet from the floor. Well, I have a ruler, so we can actually do this here. 36 inches being 3 feet. It's a meter stick, so it's not quite to the top. But I need a point somewhere in the front wall that's 3 feet from the floor. Well, what would I need to do, class? Measure up 3 feet. And that little point right there, 3 feet from the floor, right? Okay. Is that the only point that would be 3 feet from the floor? I'm way off camera here. I'm just gonna span the camera out here because I'm walking everywhere. I should have done that earlier. So this point right here is 3 feet from the floor, but it's not the only one, right? What if I came over here? Would this point be 3 feet from the floor?
Yeah, but it's not on the front wall.
Oh, but it's not on the front wall, right? So it didn't satisfy that condition, did it? There's a couple conditions here. Let's see here. Now, it's not quite in the wall, but we'll go with the chalkboard being part of the wall. That point would be 3 feet from the floor, correct? What if I were to try to find every single point in the front wall of the classroom that's 3 feet from the floor? What would I end up with? Ethan, put you on the spot. Besides chalk all over the walls, which rub off, so. All right. What again if I found every single point that was 3 feet from the floor in the front wall of the classroom?
Apart or something? Like a line?
I'd get a straight line, wouldn't I? Tell me about the straight line.
It's 3 feet from the floor.
Okay, it'd be 3 feet from the floor. Right, so it's not just any straight line, right? I could be like, straight line. There we go, that's the locus. No, it has to be a straight line that's 3 feet from the floor. And also then...
On the front wall.
Okay, well, this was on the front wall. Hold on. Is this 3 feet from the floor? Let me check. Yep, 3 feet from the floor, right there. It has to maintain 3 feet all the way. It has to keep that same distance. Therefore, the line must run parallel to the floor, right? How many were thinking a line that's parallel to the floor, 3 feet up above it? Now, we couldn't stay in the classroom if we went below, right? So we'd have to be above the floor, 3 feet above, parallel to the floor. Let's take a look at the next one. Where do you find all points in 2 side walls of your classroom that are 5 feet from their intersection? Technically, 2 side walls wouldn't intersect, would they? Assuming we mean side walls. Maybe they mean these are all 4 sides of the classroom, though wouldn't you just say walls? Anyway, that's just me being picky about the wording. So let's just say we got 2 walls that intersect. Let's go with these 2 walls. Obviously, they intersect right here. Okay? And we want 5 feet from the intersection. So in the wall, that's 5 feet away. Well, I'm about 6 feet. So if this would be about 6 feet here, let's say 5 feet's right about here. Let's just say that point, 5 feet from the intersection. Is that the only point in these walls that could be 5 feet from that intersection point? No. We could maybe find another point, couldn't we? Maybe something like right about there, right? What would we get, though, if we found every single point 5 feet away from that intersection of the walls? What do you think? Quentin?
Probably get a right angle if you went.
Well, the walls themselves make a right angle, it's true, but if I were to find all the points that are 5 feet away from that intersection.
Well, I was thinking from on that wall and on that wall and
Oh, okay, so that's true. We got to think about this wall too, don't we? So maybe somewhere about here would be a point that'd be 5 feet away. Okay.
And if you walk out from where that wall joins, about 5 feet.
Walk out from where that wall joins.
Yes, from right there, if you walk out 5 feet away.
Oh, you're saying if I just, like if I come out toward you, for instance, 5 feet, well, that wouldn't be in the walls anymore. Remember, it said in the walls, or on the walls, I guess you could say. So,
Alright, so you would get 2 lines.
I would get 2 lines, right? I get a line like this, and I get a line like this. Tell me about these 2 lines.
5 feet away from the point.
They're both going to have to stay 5 feet away from this intersection, and because they have to stay 5 feet away, that means both of them are going to have to be parallel to the line that is this corner edge, correct? So both of them will be parallel to this. Now, they're not necessarily parallel to each other because they're not in one plane, right? They're in 2 different planes. But they would be parallel to this edge 5 feet away, 1 in each wall. Good. Let's take a look at number 3. What line, they're telling us that part of the answer here, is the locus of all points in the floor of your classroom? So we're only thinking in terms of what's on the floor that are equidistant from 2 opposite walls. Let's go with the 2 side walls. Okay? Now, I'm not actually going to mark on the floor because it doesn't erase as easily as it erases off the wall. But if I wanted to find a point that is equidistant from the 2 side walls, is where I'm standing equidistant from the side walls? No. What about now?
No.
No, but certainly closer. Now I'm going to cheat. I'm going to use the ceiling tiles here.
Assuming they're
See that right there? That's 1, 2 and a half full tiles. That's 1, 2 and a half. So that'd be what, 10 feet? 4 feet, 4 feet, 2 feet. So this is a 20-foot wide room apparently. Assuming 4-foot ceiling tiles. So right under this line would be halfway between those walls, right? Is this the only point in the classroom that's equidistant from those 2 walls?
yes.
No.
Oh, the
Right here would still be equidistant from those 2 walls, right? In fact, if you were to follow it, apparently the edge of these desks all the way back and bump into Brecken's arm, that would also be equidistant. So what would I get, Chris, if I wanted all the points equidistant from 2 side walls of the classroom? A straight line. Tell me about the straight line.
parallel.
Because I could draw a whole bunch of different straight lines on the floor. I'm not going to, but I could, right?
5 feet away and parallel.
5 feet? Where'd you get 5 feet?
Or no, equidistant from the walls and parallel to the wall.
Good, it would have to be equidistant to them, and therefore, or equidistant from them, parallel to them, right? Midway in between, right? Do you have a question?
Yeah. Since they're equidistant from the same points, does that mean they're also equal? Because I know in a circle that's correct. Because like lines that are equidistant from the center are equal in a circle.
Are you talking about those 2 lines illustration? Well, they would have to be equal because to be in the classroom, remember, it said in the walls, they'd have to stop at the ceiling and stop at the floor. So they would both, assuming that this wall is the same height as that wall. May not be a guarantee. But if there's, then yes, these would have to be equal because they're bounded by space. If they hadn't been bounded, though, they would have been infinite lines. And infinite doesn't really have equal.
But this doesn't.
Well, so this line here, again, because we're staying in the classroom, it would be bounded by the same length as the sidewalls would be. Again, assuming the walls are built at right angles. But lines themselves don't have a true length. Line segments do. Lines don't. And again, if we're thinking this is a line segment because it's bounded by the front and back walls. If you didn't bind it by being in the wall within the classroom, you could think of them as being infinitely long. Let's take a look at the second part of number 3, though. What about from 2 adjacent walls? Okay, so these 2 walls, of course, being adjacent. If I were to stand right about here, assuming my arms are approximately the same length, I'm about the same distance from that wall as I am from that wall. So right here, I'd be equidistant from the 2 walls, correct? What if I came over here? Now am I the same distance from that wall as I am from this wall, class? No. Obviously, if I stood like in the corner like this, now I'm the same distance because I'm 0 distance, right? No distance at all. What about up here? Now am I the same distance? No. To keep the same distance from these walls, I'd have to walk along a line that is, Kendall, parallel to what? Parallel to these walls? So the path that I'm walking is parallel to these? I just ran into them, so it can't be parallel. Audrey, help her. Right, it would have to be, like I say, that was the premise, is it's going to be equidistant. But what if I were to draw a line on the floor, which is what it mentioned was the floor, if I were to draw the line on the floor, tracking where I'm walking, now right now I'm not equidistant, so let me get back. This looks about equidistant here. I would have to track a line, Jamie?
That would be like the angle bisector.
That would bisect the angle, because remember, every point in the bisector of an angle is equidistant from the, do you see what we're using? We're using definitions. We're using theorems that we previously memorized to help us think through these. There we go, the angle bisector would be equidistant from those two walls. Number 4, this is no longer in the classroom, obviously. It says, where are located, that's a weird way of phrasing, where are located all cities that are 3 miles from a given railroad? Well, let's assume for a moment, it's a big assumption, that the railroad tracks are straight, okay? Which means we're in Kansas. Because there's nothing in Kansas and railroad lines can go perfectly straight. In Columbus, they're working around everything. But let's just assume we have a perfectly straight railroad. And let's suppose that this city is 3 miles from the railroad. Let's suppose we have this city. Does that look like it would be 3 miles from the railroad? No, doesn't count. I hate it so much I even dropped my chalk. All right, but this city, for instance, looks like it might also be 3 miles from the railroad. Okay. What if I wanted to track, though, assuming a straight shot track, what would be all the cities 3 miles from the railroad track? Genesis?
Equal.
What?
Length.
Well, I mean, the railroad keeps on going, obviously. I just can't, I only have so much chalkboard, and I'm kind of lazy. But assuming the railroad just kept going and going and going, I mean, there could be more cities along the way that would be 3 miles away, right? What would I get if I tried to notate all the cities 3 miles away from the railroad? I would get a straight line. Assuming if this was straight, I would get a straight line, wouldn't I? Tell me about the straight line that would mark all the cities 3 miles away.
It would be Spencer Park.
It'd be who? Well, I mean, it's possible. I mean, let's just say we go into the future 20 years and now there's no more country left, which I doubt would happen. But let's just say there's no more country left and the cities have filled every space and nobody can hunt anymore, because that's sad, right? That would be very sad. But let's say we just crammed cities all over this. Well, what the shape you said would be a line, and you're right, but this would be a line. Tell me about the line compared to this railroad track. It would have to run parallel to the railroad track, wouldn't it? But again, this is a line that's parallel to the railroad track, but it's not 3 miles away, right? So I would need to get a straight line parallel to the railroad. But again, if you just say a straight line parallel to the railroad track, that's not exclusive enough. We specifically only want the straight line parallel to the railroad track that's 3 miles away. But wait. That's to the north. If this is an east-west railroad track class, you might also have a city that's 3 miles away to the south. So really, Genesis, since we could have cities, plural, 3 miles away to the south, I'd get not 1 but 2 parallel lines, each of them 3 miles, not 3 miles apart, but 3 miles away from the railroad track, 1 on either side of it. Now, if the railroad track curved, that changes the dynamic, because now the line would also curve to remain 3 miles away, right? And there's only so much you could do potentially here, right? If it were to curve in tighter than 3 miles gap between them, or really tighter than 6 miles gap between them, you couldn't have anything inside the railroad track anymore. You'd have to stay to the outside. But with the straight line makes it a little easier. Thoughts? Should we starting to figure some of this stuff out? We're going to talk more through some more of these on Monday at our next lesson. For tonight, though, there are some fundamental locus theorems you're going to need to memorize, virtually word for word. Warning you up front, You're going to need to memorize these virtually word for word. You're going to copy these theorems into your notebook for homework over the weekend. Copy pages 174 to 176. Pages 174 to 176. Those theorems and corollaries into your notebook. If you wanted to copy them on a separate page and at the top of the page label locus theorems, you could do that, though I'm not going to require it. But these are theorems you'll need to memorize virtually word for word. Not that we don't memorize most things word for word in this class, but this is even more important to make sure we get the wording exact, because hopefully you've picked up on this. Exact wording makes a big difference, doesn't it? Versus including something that should not be. All right, you are dismissed. Have a wonderful weekend.